Swayam Prabha. Digital India. Educated India.
Today we shall begin to look at various kinds of engines that actually power the aircraft to flight. You have had a good exposure to various kinds of laws of physics. We began with the laws of motion, the Newton's laws of motion. Then you had a full exposure to various kinds of laws of thermodynamics. These are the laws of physics which we shall refer to quite often when we look at the various engines, because many of these engines or all of these engines actually have to conform to these laws. If they do not conform to these laws, they cannot perform. This is the fundamental issue on the basis of which the engines are built and operated. It is necessary for you to understand that all the engines that we have today that are powering the aircraft are based on what is also known as heat engines. All these heat engines basically have to conform to all the laws of thermodynamics that you have been exposed to, and since they create motion of the aircraft, they have to conform to the laws of motion, the Newton's laws of motion. So, we have to implicitly and quite often explicitly refer to those laws of physics all the time that we are talking about the engines. To begin with today, we shall start off with looking at the most fundamental and the most probably the ancient form of aircraft engine, the piston prop engine, the kind of engine that actually powered the first flight by the Wright brothers, and almost 50 years thereafter all the aircraft flew with piston prop engines. Even today, most of the aircraft that are flying around, the small aircraft, and they are actually more in number, most of them are flown with piston prop engines. So, even today thousands of aircraft are flying around with piston prop engines, and hence it is probably a good idea for us to take a good look at how the piston prop engines work. Basically, the piston prop engines have two components. One, which is the piston engine, which can also be called some form of internal combustion or IC engine, and we will have a good look at this kind of engine basis, fundamental basis today. And later on in this lecture series, we will take a look at the propellers, which are the thrusters, which make the thrust. So, piston engine or the IC engine create the power, and the propellers convert that power to useful thrust for flying the aircraft. So, we need two components, and we will look at them separately. Today, we shall look at how the piston engine or the IC engine actually is fundamentally created, what is the basis, and we will have to go back to the thermodynamics that you have exposed to. We have to bring back the concept of energy, the concept of work, and how the energy is finally converted to useful work or power, which can finally fly an aircraft. The piston engines that we will be looking at are based on what is known as Otto cycles. Now, Otto cycles is the thermodynamic basis on which the piston engines are created. Now, Otto cycle is one of the cycles on which various heat engines are made. Almost all heat engines that we know would be based on one of the cycles that you have been exposed to. The piston engine that we are looking at is based on what is popularly known as Otto cycle. We will today look at the ideal form of the Otto cycle as was originally proposed by the thermodynamicists. And then we will look at the real form of the Otto cycle, which is how the piston engines actually work, and what is the difference between the ideal cycle and the real cycle, and this is what we will have a close look at today. As I mentioned, these cycles based on which the engines are made are also called internal combustion engines. Now, one of the reasons they are called internal combustion engines is because combustion is the method by which the energy is supplied into the system, which we call engine. Now, that is the input from outside the system into the system, and then the system converts that energy to useful work. So, conversion of energy to useful work is something you may have studied in your thermodynamics, and this is what we will now explicitly make use of in actually creating the engines. So, we would be continuously making use of the concept of putting in the energy from outside, in our case for example, by burning fuel through the process of combustion, and then we will have to find a way to convert this energy which is released by burning the fuel into useful work, and the mechanism by which it is done and finally converted to what we can call mechanical work is what the whole engine fundamentals is all about. So, we will take a look at the thermodynamics of how the engine functions, the cycles, and in the process we will try to understand how the thermodynamic concepts are finally used to make an engine that actually perform work, which is useful to us finally for the process of creating thrust, which makes an aircraft fly. As I mentioned, all heat engines are conceptually based on one thermodynamic cycle or the other. It is necessary that heat engines conform to one cycle or the other, so that you always have a continuous process of control over what is happening in various legs of the performance of the engine. And more importantly, with the use of the thermodynamic principles, the thermodynamic laws and the mathematics that goes with it, you can actually predict pretty closely how the engine is going to perform. This is very important. It is necessary for a creator of engines to know very closely how the engine is going to finally perform, and this knowledge is very important. So, it is necessary that they conform to one of the known kinds of thermodynamic cycle or the other, so that their final performances could be very closely predicted and later on closely monitored. As you know, a cycle is made up of number of legs, which are actually thermodynamic processes, and they combine together to make a cycle. Now, each of these processes could be different processes. So, one could be constant volume process, one could be constant pressure process, one could be isentropic process, so on and so forth. So, they all made up together to make a cycle, and we got to have continuous control over each of these legs or each of these processes when they are occurring, and we got to have a priori knowledge of these processes, so that we can predict what is happening in each of these legs which make up the engine together. The other important thing is these cycles which we are using for making up the engines, they use or recycle the same working medium. Now, this is very important. The working medium we have in abundance around us is air, and that is freely available in the atmosphere to us. So, all these cycles and all these engines have been created with the purpose of using freely available air as a working medium, so that the bulk of the working medium that is used for creating work, and in our case creating finally thrust, is available in air, and as a result of which all aircraft engines are essentially air breathing engines. So, we are looking at various kinds of engines from now onwards. All of them almost invariably would be air breathing engines. We shall see later on towards the end of this course, when we look at the rocket engines, those are non-air breathing engines. So, till we come to the rockets, as long as we are talking about the aircraft engines, remember we will be talking about air breathing engines that use air as the basic working medium. The cycles, as I mentioned, are made up of number of processes, and all of them have to conform to the thermodynamic laws that we have done. Each of these processes is a thermodynamic process, and they have to conform to the thermodynamic laws that you have studied over the number of lectures till now. And remember that we will be using those thermodynamic laws quite explicitly and sometimes implicitly in understanding these processes which make up the entire cycle. Let us look at what is known as the ideal Otto cycle. The cycle essentially consists of 6 processes, and let us start from the beginning. It starts from a point which we call A, and from which we have what presently let us call intake of air, and it starts from A and goes to B. So, the process A to B is called the intake of air. The air is taken into the system, and from B to C, this air is now compressed, and this is called compression process, and it goes to a higher pressure over here, as you can see in this PV diagram. And then from C, you have a burning of fuel. This is combustion process. So, in the process of burning of fuel, this compressed air is now raised in temperature to a higher level as per laws of thermodynamics. When you raise the temperature, the pressure also goes up. So, it grows to a higher pressure at D. Now, at this high pressure and temperature, the cycle now does the process of expansion. So, from D, the process is expanded, which is in engine terms is called a power stroke, and it expanded from D all the way down to E, and that is the end of the process of expansion, which is also called power stroke. And in the ideal cycle conceptually, over here between A and B, you can say that there is a certain amount of heat rejection which occurs from the system. Just like there was a heat intake into the system through fuel burning, there is heat rejection through various kinds of heat transfer, and then the process reaches B, and from B the air that has been inhaled is now exhaled, and the exhaust of the air goes out of the system, and then fresh air is brought into the system. So, this is the cycle. The air comes in, gets compressed, the fuel gets burnt, then it is expanded, the high temperature pressure air is expanded, and then there is a bit of a rejection of heat into the out of the system, and then the exhalation, the air is exhausted from the system. And this is the cycle which continuously occurs in this process which we call Otto cycle. Now, if you look at a schematic of an engine which occurs which operates as per Otto cycle. So, just below the PV diagram, you will see this diagram here of a schematic of a piston engine. Now, what happens is when the piston, this is the piston stroke as it is often called, and this is what we were calling as stroke. Now, and this is the LP is the length of the stroke. Now, what happens is over here, the end of the piston stroke, one end is called BDC. Over here, if you look at, if you take the piston in an upright position, the lower one is referred to as the bottom dead center, and the top one is called the top dead center. So, the idea, that is how the names were given, that this is the bottom dead center and this is the top dead center. The name stuck, not necessarily the pistons are always in upright position, quite often they are in horizontal position like this, but the names TDC and BDC have remained for almost 100 years. and people continue to use those terminologies. Now, what happens is when the air is inhaled, that is the process from A to B, the piston actually moves downwards over here, and this entire space is opened up. This entire space is opened up. So, air from one of the ports over here comes in and fills up this entire space, and then the process of compression starts from B all the way to C. Then the piston here, piston head as it is called, moves from BDC towards TDC. As it moves, the air which had come in and had got captured inside this volume of the piston gets compressed to a much smaller space, and as a result of which the piston now creates a very small space within which the air is now entrapped and is compressed. Now, this compressed air is then subjected to burning of the fuel. Now, this burning of the fuel then in this small space creates even higher pressure and of course, the high temperature. So, this small highly compressed air, when subjected to high temperature and pressure, then exerts huge pressure backwards onto the piston head, and as a result of which the piston is forced to move forward, and that undergoes the process of expansion all the way from D to E. And during that process, the piston head is now moving backwards, back from TDC all the way back to BDC. So, once it comes over here, we have this process of heat rejection out of the system, and then the process of exhaust starts. That means, the piston again starts moving. Now, what we have inside here is burnt fuel and air mixed up. So, what we may call burnt gas. So, this exhaust of the burnt gas now starts happening as the piston head starts moving, and this burnt gas is exhaled out of a port here. The port is timed to move to open up at this point of time, and this burnt gas now goes out through this port into the outside the system, and then the fresh charge or fresh air starts coming into the body of the cylinder. So, this is how the cycle occurs. The fresh air comes in, it is timed to open exactly when it is air is supposed to come in. Once it has come in, this port is closed down, and then the process of compression starts, and then again the combustion, and then again the power stroke, and then exhaustion or exhaust of the gas, burnt gas out of the system. So, this is how the entire cycle actually operates, that we have a continuous process by which the whole cycle does the same job again and again. Now, if you look at some of these processes thermodynamically, for example, the process A B can be referred to as a constant pressure process, because during this process there is no change of pressure. So, this is what we call a constant pressure process thermodynamically. Now, the process B to C is referred to as isentropic compression in the ideal cycle, because this process is now occurring under a thermodynamic process in which the entropy of the system is said to be conserved. So, during this process there is no change of entropy as envisaged in the ideal cycle, and the process of compression occurs along that. And then process from C to D. Now, this is combustion. Now, this occurs under constant volume process, and now during which, as you can see in the PV diagram, there is no change of volume envisaged in the ideal cycle, and as a result the combustion is expected to occur in constant volume combustion process. At the end of the combustion, we have the power stroke or expansion thermodynamically, and this is again an isentropic process, which means during which the process undergoes no change in the entropy, which essentially means that the process is essentially a diabatic and no losses are occurring during this process. Same was true for the compression. That means, these two processes are isentropic process, during which there is the processes are adiabatic, and there no losses are envisaged in the system. That means, the two processes are reversible processes. So, they are reversible adiabatic processes, which in short, or in other words, we call isentropic process. So, we have work done or power stroke, which is isentropic, work input or compression, which is isentropic. And then at the end of the process at E, we have a constant volume heat rejection from the burned gas, a mixture of fuel and air. And then at the end of this rejection process, we again have this exhaust of the fuel of the burned gas from the system, which is again a constant pressure process. It is ideally envisaged to occur in constant pressure. So, all the legs that we have seen now can be now cast in the form of one thermodynamic process or the other that you have already done, and hence all these processes are now conforming to various thermodynamic laws. So, we can now apply the thermodynamic laws to these processes and to the cycle as a whole to find out how this entire cycle is actually going to work, because finally, we want work out of this whole system. So, the entire process, that entire cycle consisting of all these processes that we have now talked about, have to now conform to various thermodynamic laws, and all of them put together finally will tell us how the entire cycle, which means the entire engine, is expected to work in this ideal process as envisaged. The net area of the PV diagram in this thermodynamic cycle diagram is sought to be increased for maximizing the power output. Now, what we can see here, this was the power stroke and this is the input stroke. So, this is the so called output stroke, this is the so called input stroke. Typically, it is envisaged or it is understood that the area subtended under this is essentially the output work. So, the entire area under the curve d E is the output work. On the other hand, the entire area under the curve B C is the input work. So, out of the output work, certain amount of work goes inside the system back again in the form of compression, and hence the difference between these two areas, that is the area subtended between B, C, D and E, essentially now represent the work that is available for doing some useful work. That is, in our case, it will be used for creating, let us say, thrust or making the engine work. So, that is the useful work that would be available, or often thermodynamically or in simple terms referred to as the net work. So, the gross work done by the power stroke minus the work input of the compression stroke is the net work that is available. Now, it stands to reason then that every engine designer would try to create a thermodynamic cycle in which the power output is, if it is to be increased, the net area that is available in this PV diagram is to be maximized. How to do that? That is another story, but the designer of the engine, he has to design a cycle first. The engine designer needs to design a cycle first, and that cycle design needs to concentrate on the concept of increasing the PV diagram, the net area of the PV diagram, so that the work output expected can be maximized. Now, how do you do that? So, the idea is, if you want power output maximized, you got to have the change of specific volume or the increase of pressure or temperature through the cycle. So, if you look at the cycle diagram, you are trying to increase this volume. Okay. Now, if you want to increase this volume, there are 2 or 3 simple ways one can do it. The length of the stroke, so to say, can be increased by which you can increase the volume, or the difference between compression stroke and power stroke, this vertically can be increased, which requires that the point D is to be raised to higher level and the power stroke occurs at a higher pressure and compression stroke occurs at a much lower pressure. So, those are the ideas by which the cycle can be designed to maximize the power output from this system. So, what it requires then is you have a large change in volume, which shall require then a large size engine. The large change in specific volume shall also require large change in pressure, and which requires again a large change in volume. Large change in temperature shall require large input of fuel or fuel of high heat release capacity. So, these are the means by which you can try to increase the work done of the system. Some of the troubles that we have is that if you want to increase the volume, you want to increase the size of the engine, it may have some limitation when it comes to the use in aircraft. So, those are the limitations which we will again look into later on, but if a cycle is being designed to create an engine, these are the issues that the cycle designer, the engine designer will have to look into, will have to contend with for designing engines that create certain amount of power or a maximum amount of power under given operating condition. Let us try to understand how the Otto cycle analysis can be done to quantify some of our needs. We need to quantify some of the parameters that we are talking about. Now, this is the cycle we have just had a look into, and this is where the heat is coming in, the fuel is being burned and the heat is coming in, and this is where we assume that certain amount of heat is being given out of the system, which could be called Q 2. So, Q 1 is the heat that is coming in. So, now understand that notwithstanding this long compression stroke and power stroke, the input to the system is through here and output through the system is from here. Okay. So, the heat input Q 1 is in a constant volume process, it is given over here, it depends on the temperature level from here to here, okay. And the heat rejection is from here, which is the temperature differential between this point and this point. Okay. We may call these points 1, 2, 3, 4, and we shall be doing that again. So, this gives the heat input and the heat output of the system. What the power stroke does is converts the heat of the energy released by the fuel burning and the pressure that is built up by the compression stroke to mechanical work or mechanical motion. So, the net work that would be available from this cycle is Q 1 minus Q 2, and this is the work done by the power stroke minus the work done by the compression stroke, what we call the net area that is available in this cycle between B, C, D, E. Okay. And that is the area that we are looking at in terms of the work done or work available from this cycle. If you look at the cycle, you would probably see there are a number of parameters that one can create to characterize this cycle. These are often called the characteristic parameters of the cycle. The first one is the compression ratio, which is the volume ratio between V B and V C. That is the compression ratio under which this cycle operates, and it is simply called this volume ratio is simply called the compression ratio. The other is the pressure ratio, that is between the pressure that is occurring between this line and this line, and this is referred to as the pressure ratio. We shall see later on that this pressure ratio has greater importance in other kinds of cycle. In this particular cycle, the compression ratio is a more important item, and then the temperature ratio, that is the maximum temperature which the cycle experiences starting from the starting temperature, and this is often called the cycle temperature ratio. So, this is the cycle compression ratio and this is the cycle temperature ratio. So, every thermodynamic cycle is actually very sensitive to these ratios, because these ratios we shall see as we go along actually decide the work capacity and the efficiency with which this work is accomplished. So, these ratios are extremely important. As I mentioned, they characterize the cycles, they are the characteristics of the cycle, and the cycles are often mentioned in terms of compression ratio, temperature ratio, and later on we will see in case of open cycles, other kinds of cycles, the pressure ratio. So, some of these ratios would be coming back to us as important parameters, and as you can see, they are non-dimensional parameters and they are very important in terms of trying to prima facie find out what could be the efficiency of some of these working cycles. Let us look at the ideal Otto cycle that we are at the moment trying to understand. That is a cycle that we have looked at, and as the compression and the expansion processes, as we have seen, are isentropic, we can use the isentropic laws that you have studied, and then we have the combustion and the heat rejection processes, which are constant volume processes, and we can use the thermodynamic laws that you have used for those kind of processes. And if we use all of them, and we can sit down and do a simple derivation, what you can find is the cycle efficiency can be written down. This is the thermal efficiency of the cycle. It can be written down in terms of the compression ratio or the volume ratio and the specific heat ratio that is of the working medium that we are using. In our case, that is air. If we have just these two values available with us, that is the compression ratio and the specific heat ratio of the working medium, we can quickly find out what the cycle efficiency would be. So, you see it is quite simple that if you prima facie have the compression ratio available with you, you know the working medium that you are using, you can quickly find out what the cycle efficiency is likely to be. And as we shall see, this allows the cycle designer, the engine designer, to indeed configure a cycle or configure an engine even before it is actually built. Using this, for example, we can put down some numbers. This is the compression ratio, for example, the cycle designer or the engine designer is trying to build, and if you have these kind of values, these are the thermal efficiencies with which the engines will work. Now, I have used here two different specific heat ratios. 1.35 is what is quite often used for hot gases, or when the fuel has been burned quite often, that is a kind of value used. 1.4, as you might know already, is normally used for simple air. So, if you use those specific heat ratios, you get various values of efficiencies, and as you can see here, as the compression ratio increases, the efficiency of the cycle and that of the engine actually increases. If you have a pure air, of course, the efficiency is a little higher, but as you know, we have to burn fuel to put in the energy into the system, and hence this is the kind of value that we are normally likely to encounter in actual engines. And that gives us an idea to what extent you can have high compression ratios to get higher and higher energy efficiency of the engine. What the compression ratio can be depends on number of parameters or number of practical considerations, and we shall be talking about some of that as we go along in this lecture and in the next lecture. So, the cycle designer has an idea now that if he chooses certain compression ratio and given the working medium, he would be able to attain certain kind of cycle efficiency, which he hopes to come pretty close to in an actual working engine. Now, the PV diagram that we have looked at can also be recast in the form of what can be called, what is often called the TS diagram, which is of course, as you know, the other way of diagrammatically representing a cycle. So, cycle is often represented either in PV diagram or in TS diagram. And in this case, if we cast the Otto cycle in the form of a TS diagram, to begin with, for example, we have written down the efficiency, thermal efficiency all over again. And in the TS diagram, we can now see that the work done, for example, if we take the first cycle here 6, 2, 3 and 5, and that is the work done of the system or the heat input into the system, and heat output Q 2 is in terms of 6, 1, 4, 5. Now, TS diagram directly tells us the work, the heat input and the heat output of the system, and as a result of which the thermal efficiency can be quickly found, and it tells us again that the net area, that is 1, 2, 3, 4 actually gives us the net work output or net energy available for work divided by the net work input or net heat input, and that is thermal efficiency of the system. Now, let us consider in this TS diagram another cycle which has same net area as the first one, that is the area 1, 2, 3, 4 is same as the area, let us say 1, 7, 8 and 9. So, these two areas are exactly same. So, two different people, let us say, have configured two different cycles, and the net area of both of them are actually same. Okay. So, let us say two designers have created two different these two different cycle. What happens is, in the second cycle, which is 1, 7, 8, 9, 1, this actually would have a higher efficiency, and this higher efficiency is because this area 6, 1, 9, 0 is actually less than the area 6, 1, 4, 5. That means, the heat rejection in the second cycle is actually much lower, and as a result of which the area 6, 7, 8, 1, 0, that is 6, 7, 8, 6, 7, 8, 10 really 6, 7, 8, 10 is actually higher than it is also the area 6, 7, 8, 10 is lower than the area 6, 2, 3, 5, 6, 2, 3, 5. So, as a result of which the efficiency which is now given in terms of the net area and the heat input into the system, because of the fact that the net area of 6, 1, 4, 5 is actually higher than the 6, 1, 9, 0, the efficiency of the second cycle comes out to be much higher, which means if you can do the heat input at a higher pressure. Now, this is the higher pressure line in the TS diagram, 7, 8 is a pressure line, constant volume line, sorry, and that constant, if you can do that, the heat input at a constant volume line, you can get a higher efficiency of the system, even if the area net area is same. So, which means the cycle design or the cycle designer who looks into creating the cycle has a very important role to play in finally creating the engine that finally is out of various kinds of materials. So, the conceptual cycle that the Otto cycle is designed on creates the engine, and a lot of thought needs to be given to creating the Otto cycle, which finally creates the piston engine that works and that supplies power for creation of thrust. Let us now turn our attention to what could be called the real engine or the actual piston engine, according to which the actual engine would work. Now, some of these things are born out of the understanding of how the piston engine actually works, and as a result of which we shall see here that the what we can call now a real cycle, let us say conforming to some piston engine, differs quite a lot from the ideal cycle. The difference is, for example, you can see the net area that is created by the real cycle seems to be substantially less than the net area that was being created by the ideal conceptual cycle. This is due to the fact that the work which is being done during the expansion compression process quite often are not isentropic. You remember, we had assumed that the processes are isentropic, and as we shall see as we move along more and more, that these processes cannot be isentropic. Quite often they can indeed be adiabatic, they can be pretty closely adiabatic, but quite often they are unlikely to be reversible processes. So, we are going to have processes which are mostly irreversible processes, which means they undergo certain amount of loss. This loss is in the form of loss of energy, and as a result of which the net work that is available outside of the system, out of the system, is going to be much less than what is conceived in the ideal cycle. And as we shall see here, that the intake and exhaust processes are not on the same pressure line. These are the reasons because of which the real cycle differs quite a lot from the ideal cycle. Let us get into them a little more in detail. The intake of the fresh air, let us start from the intake, often happens at a pressure which is 1 to 2 and which is often a little lower than the ideal cycle. And as we shall see later on, that the exhaust often happens at a pressure higher than that of the ideal cycle. It starts from here and it goes around here, and then this is how the intake occurs. Now, this is how the air is driven out of the piston, and this is how the piston actually takes in the air. And as a result of which, there is a slight difference between the exhaust stroke pressure line and the intake stroke pressure line, and it creates a certain amount of work that goes away in the process of exhaust and intake, and that would not be available to the external agency which requires that work for creating thrust through the propellers. So, the intake and exhaust do not conform to the ideal cycle concept. Now, let us look at the compression process. The compression that process quite often, since the intake process finishes its intake line at 2, which is, as you can see, a little lower than B, the compression process starts at a pressure which is lower and quite often proceeds along a line, a centropic line, which is a little lower, and as a result of which it quite often, and as a result of the fact that it does not conform to the reversibility and it encounters certain amount of losses due to the motion of the piston inside the cylinder, it does not quite reach the point C. The compression process often goes up to C, up to 3, and then at 3 the combustion is initiated. So, the compression process, the only compression process as we know, goes from 2 to 3, and at 3's a combustion is initiated, and this combustion starts at 3. The compression actually continues a little. It goes to what we had called TDC in the piston, and then the combustion process continues up to 4. So, the pressure and temperature keeps on rising, and then over here the expansion process starts. So, the process of combustion, as you can see, quite often due to the process of either incomplete combustion or due to the fact that the movement of piston has somehow come in the way, it never quite finally reaches the point D. Somehow or other it finishes off at somewhere around 4, and then the process of expansion or the power stroke starts. This expansion process now starts, as you can see, quite often somewhere over here, which means the expansion in some manner has started even before the combustion process is actually completed. And from here we can officially say that the expansion has started. Now, by now the fuel has been burned and we have a mixture of fuel and air, and then this power stroke starts at pressure 4, and this high pressure now moves the piston down to 5. And as we can see slowly that it finally it starts at a pressure lower than D, it finishes off at pressure eventually which is lower than E, and over here as we shall see that the power stroke actually takes a round over here. Quite often you do not have much of a time really for the heat rejection process, which is ideally conceived or envisaged, and as a result the exhaust process starts right away here, and the heat rejection process, which is shown from E to B or E to F, is quite often very quickly almost instantaneously rounded out over here. In fact, the exhaust gas that is going out carries away the heat. So, the heat rejection often happens with the exhaustion process, and the exhaust gas or the burnt gas that is going out actually carries away a lot of heat. So, the ideal process and the real process, as you can see, happen quite differently, because the motion of the piston, the burning of the fuel, all of it together finally creates what we call the real cycle. And this as a result of which the exhaust process is completed when it reaches 6. Now, this often occurs, now you can see, at a pressure which is at a higher pressure. It starts off actually, as I mentioned over here, a little after 5, and then as a result of which it settles down at a pressure which is exhaust pressure which is at a higher pressure than the ideal pressure envisaged, and it ends up at 6, and then the intake process starts all over again. So, the whole cycle of the engine starts all over again. So, this is how the real cycle operates, and this is how the real cycle is quite often different from the ideal cycle. This particular cycle was initially used for creating what is known as two-stroke engine. Various kinds of two-strokes engines are operational even today. However, the two-strokes engines are not used in aircraft power plant anymore, and all the modern aircraft engines use what is known as four-stroke engine. Now, very quickly, the two-stroke engine, what used to do, or wherever they are used even today, they kind of combine the intake and power stroke, and then they combine the compression and exhaust stroke, and somewhere in between the combustion is expected to occur in a very short time when the piston is at TDC. So, this is a kind of hand drawn sketch of a two-stroke engine. So, when this reaches the top over here, the combustion is expected to occur, and then the power stroke could occur, and when the power stroke occurs, the intake also starts coming from this side. So, this is the side from which the intake comes, and when the compression stroke occurs, the burnt gas is simultaneously exhaled out of the system. So, this is called two stroke because the two legs of the cycle are combined together into one stroke, and as a result this engine operates on two stroke principle, whereas as I mentioned most of the engines today are 4 stroke. So, from now onwards the cycles and other forms of engine that we look at would be 4 stroke engines. This is a kind of 4 stroke engine that is used in the modern aircraft engines, all kinds of modern aircraft engines. Let us quickly understand how the thermodynamic processes are converted to what we call now strokes. The familiarity of the engine, very quickly, we have an intake valve over here which opens this intake port through which the fresh air comes in, and there